but at the same time, we're controlling for the increase in complexity by adding more dimensionality to the system. We're saying now that we can compare one system of one dimensionality to another system of a different dimensionality, and R squared will still be the same relative quality metric, right? R squared previously was the only thing that we could compare from set to set because there was, it was a sort of unitless with respect to values. If we go back to this slide, you'll see, if you look over there on the left-hand side, notice those are really weird high numericals, like starting off at 10,000 and going up to 30,000, right? R squared is just a 0 to 1, right? It's effectively a probability of fit. So what we think about with R squared is actually, to go back to the definition again, R squared, and I don't use it just typically when we first talk about it, I typically just say it's a quality of fit metric, but the way in which R squared is defined is the degree of variance that is captured by the model, right? The quantity of variance that's captured. So the value here says that if more variance is captured, we have that diminishing return of capturing too much variance of too many dimensions. That says that I penalize the summation residual square divided by how many dimensions I'm actually adding to it. So if I need to add too many dimensions, let's say this, so let's back off of that. Say, if I add too many dimensions in order to try to capture the variance to a certain degree, it has that diminishing return quality that as I add dimensions, this adjusted R squared, that fraction is going to get bigger, right? So it's going to keep going down. Previously, RSS was divided by TSS. We're trying to create a balance between the known characteristic, TSS known characteristic based upon the mean, right? The biasing coefficients. So I have the variance capture and the bias coefficients. So if I say I maximize bias capture as well, or maximize variance capture, minimize bias characteristics, the balance here is related to, as D increases, the numerator of the fraction portion of RSS is going to blow up. What ends up actually happening that we note here is that since RSS is likely actually decreasing as a result of every time we add D, should be, right? Because it should be, more features should provide more capture, but at the same time, it still caps out, it still levels out at an absolute sort of maximum value. Notice something that's what happens with the Bayesian information criteria. So let's compare BCI and adjusted R squared. There is an ever so slight drop off adjusted R squared past the max point. It's tiny. As a matter of fact, it's really actually kind of hard to see there. There's a tiny, tiny drop off. Whereas BIC does what? It goes back up. Right. It's pretty substantial. The reason why I say it's not like crazy like the first few were, but it's not like a crazy divergent drop like tipping back up that way. But that's because of the fact that we're only really testing it with a small subfraction of the internal data set. So we're only testing it with like 20% at a k-fold of 5. So this testing variance is a result of the inherent overfitting characteristics of the base model. So as it gets too much dimensionality, too much flexibility, it overfits. And we're trying to avoid that. We're trying to say, what can we do to ensure that we don't overfit? So most of these tools really are just mechanisms that allow us to be able to say, what is a reasonable degree of flexibility with respect to the scale of the data set. I would say Bayes is probably best if you have really small data sets and you need a very aggressive methodology to ensure that you get only the absolute bare minimum. CP criteria or ASC are good sort of overall. In general, they're a good balance between removing features, right, or paring down on features and getting good quality of fit. fits, and then adjusted R-squared is usually more to compare model to model or across data sets with respect to the amount of time that you're sort of doing this process. How many times are you doing this, breaking it up, looking at it, redoing it? R-squared is going to be consistent across every version of it that you create, right? So you're going to be able to say the lowest adjusted R-squared is likely to be the one that has, or excuse me, the lowest error with respect to adjusted R-squared is larger R-squared. Lowest error. So we say here that the argument here is that unlike R-squared, standard R-squared statistic, adjusted R-squared pays a price for the inclusion of unnecessary variables, all right? I said this one's relatively straightforward in terms of explanation. This is one thing that's interesting about this is adjusted R-squared provides a direct estimate of test error and does not require us to calculate an estimate of the error, a variance-related error, right? So it doesn't require us to calculate sigma squared. What advantage does that have? Well, it's just computational complexity advantage. The reason why computational complexity would be the part I'm talking about there is, in order to how you calculate that, you have to go through the entire data set to calculate standard deviation. So that's a chunk of statistical work. Whereas if you look, there's no statistical characteristics that aren't handled here, but we're not really spending any extra time on the direct compute because RSS and TSS are already calculated. We calculate TSS in order to determine our bias characteristic, and we calculate RSS as a result of the summation of all the error with model consideration. So we're already taking into consideration the variance of the data sets to the model, so we don't actually have to calculate the sigma square like we do with the BIC and Malus criteria, right? We have to calculate this value sigma square. Notice it's got its hat on, so it's it's party, and it's figuring out the variance characteristic of the system. So we say that R-squared can be used in a wide range of model selection tasks generally, because it doesn't really suffer from some of those targeted issues we have, but it's not effective, it's not super effective for anything besides linear modeling. We still are going to have to use AIC criterion for our classification type tasks. There's really nothing besides classification here. So what I say, why are we always focused mostly on linear? Why do we have 3 different linear models and only 1 methodology for classification tasks? Because reducing features for classification tasks takes a different strategy and a lot of different tests, right? You can simply use k-fold methodologies with quality of fit metrics rather than having to try to apply this. But we're also going to come up with a couple of tools, and that's going to be these shrinkage methodologies that work quite a bit better for classification tasks, right, with respect to which features we're keeping. So it says here that it is, last line says, it's hard to estimate error and variance. Why is it hard to estimate that? Because you need a lot of samples in order to estimate the error variance. It's not a simple task. We're only going to get something that is an approximation. Remember also, from k-fold to k-fold, the error variance is going to be unique to that fold. So it's not going to be consistent. So it's an average, it's an estimate, it's largely either an overestimate or an underestimate. So the methodologies that use it, Malus and BIC criteria, are pretty dependent on the quality of that measurement, whereas R-squared is not quite as dependent on the quality of the measurement. I know I'm talking up adjusted R-squared a lot, but yeah.
If it's that important, how do you make sure you're getting a good estimate and average? Or is that just a shot in the dark? There isn't really such
thing as a good estimate. All right, let me explain to you the reason why.
How do you know
Your
if
estimate
you
is
can trust it? I guess I should reword my.
Trust is relative. Trust is relative. The size of the data set is going to be contingent on the quality of the assessment, right? So the internal variance of the data, if the internal variance of the data is high, then we're going to expect high error variance. Effectively, the error variance we're talking about here is from the training portion of the K-fold to whatever its internal validation set is. Think about it in that way. Every time that I shift to a new, this is the testing subset, this is the training set, right? This is training, this is the testing over here. Those two have variance in the error, right? So one model is going to be sort of better at predicting the internal validation set. How do I do that? Well, I'm calculating across K folds. Well, if I do K fold of 5, I only have 5 different sets of testing and training to compare against one another. So effectively, the sample number is always going to be 5 in K fold of 5 with respect to variance estimate. So it's still a small number of sets to sets comparison of which to estimate the total variance in that error. We're going to talk about something that we call bootstrap, and it is a mechanism by which we compute that relatively directly for the entire data set. So characterizing the error variance against the alpha of the bootstrap is probably a good way of confirming that estimation, right? You remember we said we needed something to allow us to sort of give us an upper and lower boundary on the likely accuracy of the system. That's effectively what K-fold does, but the bootstrap does so in a more comprehensive way. We'll talk about bootstrap. That's probably the best answer I can give you at the moment, just kind of off the top of my head.
Okay.
Just knowing that when you look at it from a calculation perspective, how is the variance established? It's effectively a ratio of differences between means.
Right.
So the relative variance characteristic is the quality thereof should increase as the distribution starts to mirror the actual real life distribution. So it's going to be a quality of sampling, how well the sampling is doing at capturing the variance within the population. We can utilize stuff like students test, right, or chi-square estimates to be able to determine the variance capture, but those are only going to be as good as, like I said, they're only as good as the data you get. So it's a multi-comparison state. Key factor, realistically, key factor at the end of the system is external validation. So I use that term now because I think I used it once or twice, but I'll try to use that term consistently from now on. The test set that is held out at the very beginning of the process of K-folding is called the holdout set, right? Or the holdout validation. It is often called the test set, and then the internal sets are sometimes called validation. But none of that is consistent and none of it is guaranteed. So I try to tell you all the ways in which you could find it, from subject matter to subject matter. If you go from electrical engineering publications to computer science publications to more of the mathematics publications within AI and machine learning research, you'll find slightly different standards with regard to what terms they use in what spaces. Because what they're doing is they're drawing upon the corpus of published works in order to establish the standards and processes of UK. So I think, like I said, once you recognize sort of what all the things that can be called, sometimes you get a better picture in your head of what it really is, right? So you think about the holdout validation set, or the holdout testing, is the final case in which we effectively simulate what it's like to see new data, right? So the holdout validation, the K-fold methodology, does internal processes to determine what is likely to happen, right? To predict what the performance will be outside. But the outside performance ultimately speaks to whether or not the model we constructed is capturing sufficiently the underlying variance in the system. Okay, let's go ahead and move on. I want to go to, all right, so this is, we already talked about this. This is mostly just an explanation of that. If you want to understand a little bit more of what's going on with the pictures, with the figures, this explains kind of what's happening there. K-fold to 10 for validation and looking at the changes in the model methodology. I want to talk about shrinkage methods today, and we're probably going to get ahead of the other class because of how I worked it out this week, but that's fine. So let's first start with something that's kind of funny. The first half of this chapter tries to deal with removing additional unnecessary features, all right? We do so in an iterative way. We choose which ones we include, which ones we exclude, based upon certain characteristics of the performance, effectively binary on and off switch, right? Just everybody hits a switch and determines whether they're included or not. Shrinkage methodologies utilize all P, right? So we don't actually reduce or remove any of the features when we start the model training process. We're going to change the model's inclusion or exclusion of a feature in a slightly different way. So rather than just binarily turning it on or off with respect to the construction of the initial multivariate model, we're going to give the model the capacity, or as we're going to say, we're going to give the model the impetus, if you know what that term means, right? Impetus is like the necessity. We're going to create in it a need as a result of a penalty. So we've been penalizing these systems already. We talked about penalties. What was the penalty for inclusion of additional features previously? Right, for AIC is 2D sigma square, 2D variance. BIC is log n of the variance, or log n of D variance, right? And then for adjusted R squared, it's reducing or ratioing RSS relative to D, right? So the more D increases, the more that ratio starts to offset. Regularization processes, all right? It says it regularizes the coefficient estimates. So if I said to you, what is the difference between removing a feature and setting its coefficient to 0? Question. There isn't a difference. All right? There isn't a difference. If I multiply something by 0, it might as well not be included, okay? There are some programming strategies and even some methods, and we'll talk about the second one, that will actually do this, all right? So the first one we're going to talk about is, we're going to talk about L1 and L2. We're going to talk about L2 first. Why? Why we're going to talk about L2 first? I don't know. It's because of how it works. So it was actually kind of invented in this direction. L1 was given the name lasso for the purpose. But we say that effectively these two methodologies are a mirror of one another, in which the strategy of the dimensionality impact is to mitigate the relative coefficients of the features and utilize that as a factor in scaling the model. So if I add a certain amount of the inclusion of that feature's coefficient, rather than just the inclusion of the feature, I can incentivize the model to reduce the coefficient. All right, so let's look at the formula. Let's look up top. Don't freak out about the top, you've already seen the top, okay? You've just seen it in other forms. What is up top? Residual sum of squares, right? This is literally the least squares model. So least squares model takes the summation. What's the first summation there on? Well, let's go from the right and look what's inside the parentheses first. What's happening inside the parentheses? Well, we have y, that's our target, and then we have beta naught, and then beta j x sub ij. And that's inside of sigma for p. So j is the iterator for p. All right, now let's go over to the other sigma on the outside. I is the iterator for n. So we can read what's inside the sigma over here on the other side as beta p index, right, for x of n index p. What do I mean by x of n index p, or x of ij over there on the right hand side? That is the feature for the sample, right? So individual feature, individual sample. So this allows us to do the regression in a multi-dimensional way. So this is just the effect of multidimensionality. It's saying that I'm going to sum together the linearities as a result of that target, and then subtract them from the target. So y is that y actually contains y for I, or y for j. Let's just say y for j, with respect to that target, right? So each individual feature will have some contribution to Y. That's the argument we're making. What is the argument? What is the strength of that argument, right? The strength of that argument is its capacity to reject the null hypothesis, something that indicates that the value that we get at the target for that particular sample number, effectively it says yi there is what? It is the nth target for the nth value of the set of features, of the array of features. What does that array look like? We often call it a feature vector. So just going to go back to our idea that we say x of 1, x of 2, x of 3, x of 4 are all 4 features of the first sample. So we're going to say that we have now a 4-dimensional model, and we want to target back to the original input. Well, everything's fine here, right? Let's copy that down here again. But now we've added something else to it. This is actually the formula for what is called the ridge regression, or L2 regularization, right? And it's pronounced like ELL, like the letter L, right? We say, oh goodness, this one doesn't work either. Let me grab that, I think. Say L2, right? L subscript 2, or just LN2. So L2 regularization is ridge regression. Why the 2? The 2. The square. Okay? That's the difference between L2 regularization, L1 regularization. So that's the key feature to look for. If you're looking at one of these equations, you say, how do I know which one it is? You'll see the big reason why is because that square matters as to how the system ultimately works. But let's look what's right here, okay? Matter of fact, we can just say we've added something onto it, and so let's just restate it. This whole slide can be summed up right here, okay? This is actually the thing we're interested in, just this portion. It says RSS plus the penalty, all right? How does a penalty factor in to changing the model? Well, if we're assessing or if we're quantitizing the sum of all of the coefficients, because now we're doing what? We're iterating through all coefficients of P. So this means if I have the model, right, I have beta 1, right, for x1, beta 2 for x2, beta 3, x3, right? Everybody good with this? It is the summation of just the coefficient factor, all right? It's not the product of these things together. It's not the quantity that would go into the linear equation, right? The quantity goes into the linear equation. That's already handled by RSS. What I'm actually doing here is I'm just saying, just add the coefficients together, right? But I'm going a step above that. I'm saying, add the squares of the coefficients together, sum them all up. I'm getting some weird looks. That's right, I'm glad that you understand what I'm talking about if the weird looks are coming to me, all right? The reason why I say this is because on the first slide up there, I didn't read it, I'm gonna state it now, is this is weirdly counterintuitive. And I'll explain to you the reason why it's counterintuitive in a minute. This is one of those things that took me a while whenever I first studied it. I'm like, what? How? Why? That sounds stupid. Why are we doing that? Okay? You think you'll get a feel for it in a bit. Yeah. You already hand up, did you? Oh, I think. So I'm squaring the coefficients. What's this going to do? What's this going to do as a factor with respect to RSS? What's the model going to be incentivized to do to the coefficients now? The goal is to minimize this sum, right, between RSS and that factor, lambda, right? So lambda is our first time we get a knob. We get to crank, get to turn it up and down and see which way it goes, right? Make lambda bigger and you rescale the penalty. Makes lambda really small and the penalties, that's okay. I mean, the one coefficient got bigger, but it's not that big of a problem, right? Crank it way up and the system goes, whoa, you move that coefficient by 0.001. slow roll, all right? You know, getting crazy in here with it, all right? What's the point of this? This is a weird one. Let's say we have a graph, and we have a relatively linear relationship between a series of points. We would say fairly easy to do this, right? I can just go ahead and draw my line. Yeah, that's gonna be low, relatively low RSS, right? But let's imagine we did something else. Let's imagine that somehow we actually got a training set that only consisted of, let's say, these 2 points. Where's the line going to go now, right? It's going to minimize and go straight through those 2. I know I'm drawing it kind of crooked, but it's all right. You imagine those are linear. It's straight. What's going to happen now to all of the other points? If I treat all of these points now as the testing set for the ones that were part of the training set previously, what's happened? Wow, the variance between the testing and training is very high. The actual error within the training set is very low. Simply because of the fact that I had a low number of samples, or because the particular training set that I selected had a higher coherence, it didn't really teach me the underlying relationship between those factors in the system. So what's happening with this line, right? What's the coefficient of this line? Right? So rise over run, right? That's our slope. So what happens whenever I say I'm going to scale it by lambda of the beta squared, right? Coefficient squared. So rescale, I'm going to rescale the quality of the beta, add this to RSS. The higher that slope is, the more towards vertical it is, the more direct the relationship argument is, the more I'm going to penalize it. Watch what happens. If I add some scaling factor here, then I'm actually going to build a new line that's going to compensate for some error, right? It's going to say, well, let's not make the correlation, let's not take all the correlation we see within the training set at complete face value. Let's actually relax that correlation a bit and see whether or not, if I try to relax that correlation a bit, I can stop the model from overfitting. Right? I say, don't get crazy with your correlations. So the absolute highest lambda would be what? It'd be this. It would be this, because what would happen? The coefficients would go so close to 0 that you'd be left with just the intercept term, right? You'd be effectively left with the null hypothesis, H naught, right? Beta naught term. You'd be left with the mean of the target. But anything that is a lower number, as lambda decreases, it sort of allows the system more and more flexibility to be able to adjust and change the slope of it, right? Say, yeah, you can have a little bit of slope, right? You can have a little bit of correlation. Now, why would if I'm talking about realistically 1-to-1, I'm talking about a two-dimensional system, right? This is the horizontal to vertical axis system. I don't really need to use this here. Why? Because I don't really have a feature problem yet. I don't have a feature problem yet. A lot of people will show you this example, right? This is the common example of how it works. But I'm going to tell you that it's a vast oversimplification in the effect that the main use of this is when this is a high dimensional space. So in truth, while the goal is to try to relax it, to try to get it to fit for a better target, the actual overarching goal, and this is one of those things that would take you a long time to find in a similar way. All right, so I do encourage to pay attention to this because I don't necessarily publish it. All right, so you guys get the inside track on why this actually matters. Imagine that I have several different features. right? Each one has this slight correlative characteristic. And with respect to that high dimensionality space, this problem actually does start to loom really large, right? Because at high dimensions, we don't have very many supporting elements in that space. We're spanning long distances with really small conjectures. So, if I say that you need to use all the information at your capacity, right? Let's think about it this way. I have a model of, let's say, rainfall, likelihood of rainfall for a day. If you calculate, sort of reverse propagate from the information you have for rainfall likelihood, what's one of the highest correlated elements you're going to see? Just the humidity, relative humidity, right? Relative humidity is a good indicator, but it isn't always the only indicator, right? Most of the time it'll be there, it'll be a good indicator. But if I write my linear equation such that the coefficient of relative humidity is the biggest term in that whole equation, that basically means that I'm putting all the weight on the likelihood, the future likelihood of rainfall to come from high humidity time periods. When things like barometric pressure, wind speed, wind direction, ground temperature, right? All those factors can be influencing of the actual rainfall chance. So what happens whenever I say, let's minimize the impact of the coefficients? I'm actually encouraging the model to be more democratic. I'm saying, look, don't focus so much on this one guy, okay? I know he's a good indicator. I know it's a good barometer, right? But at the same time, it's not everything. It's not everything. Go look for some correlations elsewhere. So I'm going to make you pick out your correlation a piece at a time from several different spaces. I'm going to incentivize you when you find good correlations, because I'm going to allow you to be able to increase that coefficient, because guess what? As long as you reduce RSS, then you can increase that coefficient, because it's the sum of those two terms. It's not simply the raw increase, right? It's just the penalty factor. It can get bigger. You can make it to have a slope, right? As long as you prove to me that it really, really needs it. That's effectively the thing. It's a balancing act. We have a teeter-totter again, right? A teeter-totter between increasing the coefficient quantity, like the scale of the coefficient. Effectively, what is the scale of the coefficient in this case? It's a measurement of significance. How significant is that feature? How much does it play into the system? So if I try to make everyone equally significant, right, that's how I'm doing it. That's what I'm doing here. And like I said, this explanation is one of those things where I say, yeah, maybe I'm skipping a couple of steps in the process. But that square characteristic there does what? It says, as it gets closer and closer to zero, what's going to happen? Less and less impact, right? Tiny number times a tiny number gets smaller. Big numbers, what's going to happen? They blow up, right? So the moment it goes down below 1, it starts actually getting smaller. So you theoretically could have a system that had relatively equal likelihoods, all at 1.0, right? 1 times 1 is 1. Effectively, their squares don't really matter at that 1 point. Anything below that, their squares start to even diminish further. So it's only whenever coefficients start to get large, up into the positive numbers, and the scalar starts to overemphasize. This is a mechanism to stop overemphasis of features that seem both quantitatively and correlatively higher linked, so that we try to find correlations and characteristics in other features that might have more tacit, more fringe intercorrelates. We want to tease out all the data out of the system. Ridge regression can actually improve the performance of a model, even though we're actually reducing or minimizing the summation of the square of the coefficients. Seem like magic to anyone? Sorcery, okay? That's all I say about this. Whoever figured this out, freaking evil genius, okay? I'm just saying, evil genius at play here. But when you start thinking about how it actually works, you go, huh, it's actually not so bad. Like, it's kind of weird when you do it. But what's going to end up happening? Are you ever going to get rid of any feature here? No. As I said, as they get closer to 0, they're going to be so disincentivized to continue to reduce them, right? They were incentivizing the model. We got out our whip, right? We got our chair and our whip, and we're taming the model, right? So as we crank lambda up, the model gets more and more, it gets more aggressive about controlling the behavior we don't want it to have. So we've effectively, anytime that you create a metric, a methodology by which to guide the model toward your objectives, toward your goal, you can create new methodologies for improving models. It's all right here. Can't really change this. This is we're kind of stuck with this. This is the overarching objective of the system. But you can tack on new things onto the end of it to try to say, okay, I want you to focus on this specific aspect of the overall error estimation and guide it. You're giving it a rule of thumb. Okay? This is effectively a heuristic. It's sort of a generalized rule. Generally, we need to minimize these things below normal, so we create uniform significance. You can build a lot of stuff over there, all right? There's a lot of what we call loss metrics or loss factors, right? So we try to get the system to minimize the loss in the characteristics. So the penalty, or a loss penalty, is built in to this target metric. But we always want to make sure that there's a positive tuning factor, and we always want to make sure that it's something that's not overly aggressive with respect to model. Yes?
So then do we just iterate through a specific range of values and see how?
We iterate through N.
Oh, through every single?
We iterate through N. We go back through the data set over and over again. So previously we haven't had any need to because we converged to the ideal minimization the first time we ran through it, right? Now we have a multivariate, a high-dimensional multivariate. How many solutions are there? There are theoretically an infinite number of them, right? So depending on the integration and rescaling, because there are n equations and m unknowns. Whenever there are more equations than unknowns, it becomes ill-posed. There could be theoretically multiple values that could satisfy, but none of them will satisfy all. That's the variance capture characteristic. So no answer, no one set of coefficient answers will satisfy all of the different samples with 100% accuracy. So since we're looking at it from the perspective of trying to find the one underlying system that makes everybody equally unhappy, that's really what I say. That's the whole job of the machine learning engineer, is to do compromise. Compromise is where everybody leaves the table equally unhappy. All right? So if we spread the blame around, if we make everybody slightly uncomfortable, then we've done our job well, because we've come up with a solution that doesn't make these people better off, these samples better off, and these samples worse off, but we are very much, it is the hyper-democratic mindset, right? Everybody equally represented. In this particular case, we iterate through, we say, okay, here's the first assessment I had, this is what I got based upon these coefficients. But what happens when you adjust the coefficients? Now you say, well, I got a new error, right? Now I have to iterate through again in order to attempt to rebalance which of the coefficients have which term spacing. And I'm going to be incentivized to reduce RSS, but I also have not just RSS, but all of the scaling factors of the penalties for the coefficients. They increase the multiple variates we now have to be able to play with to try to minimize the equation. So now one factor is the coefficient times the feature, right? But now the coefficient times the features RSS are there on the left. Now we're including an additional metric where we're isolating the coefficient by itself, right? So we're actually double optimizing based upon the notion of the coefficient. Not only do you want to make the RSS globally low, but you want to make the sum of the squares of the coefficients globally low. What does that look like? It looks like you're going to have to go through it multiple times. You're going to have to guess, check, guess, check, guess, check, update. This is an iterative process. You're going to change the values and keep going through the samples until you reach a global minimum, right? We can use k-fold methodology for that purpose to be able to create multiple different versions of it. Okay, everybody good with that? Does that make things clearer? What did I do here? Okay, I went forward slide.
Until Monday anyways.
You're clear till Monday?
And then I'll need you to refresh.
All right, so we're gonna talk about briefly, and I said we actually didn't get very much further than I anticipated, because this ridge regression is weird enough that it does merit some time to talk about, right? We've already talked about this. Shrinkage penalty, or a scale penalty, right, or loss metric are terms we use here, and we use lambda as a control factor. I don't know what this means. I've looked at this plenty of times, and I don't really, this is how they try to explain what this does. Let's just ignore that for the moment. There is another slide that I found that's slightly better, but what actually ends up happening here, usually is in high enough dimensions, you have to show it as like a surface, and the surfaces are really weird and hard to interpret, okay? So let's just stick with what we said, which is to try to make everybody equally contributing, try to take everybody's voice into consideration when it comes to the features, all right? We use this term, predictor standardization, as a mechanism for applying ridge regression methodology. Effectively, this is a relationship of standardization based upon rescaling everything within the range of the mean of the predictors. Have you ever heard of normalization? Right? This is just normalizing the predictor. So it tries to normalize the variance. There isn't much difference between these, but like I said, I want to focus mostly on ridge, and then I want to mention lasso briefly, all right? Lasso. Least absolute sum of squares operator, right? That's what it stands for, according to one thing. I don't know if the original author intended it to be sum of substances operator. I don't really know, but I've seen it mostly as sum of squares operator. So when I say least absolute sum, I'm talking about least absolute sum of squares with respect to RSS. So don't get confused when I say sum of squares operator as to mean that this is the squares of the coefficients, because I don't use the squares of the coefficients in this one. This one is L1 regularization. The 2 refers to the square, all right? The L1 operator refers to just the linearization of the coefficient characteristics. What's different in this computation?
Absolute value. You're making everything positive.
I'm making everything positive. And what happens with absolute value when I add it as a penalty? What happens at 1? What happens when it goes below 1? Previously, 1 was where it stopped, where it had the reverse direction, right? Where the coefficient started getting smaller by taking the square. So the rate at which it converges to 0 in the square is going to be slower than the rate of the absolute value, right? Because as it gets smaller and smaller, small number times small number is smaller number, is going to be less penalty. Absolute value is more penalty. The lasso is the most aggressive, all right? The L2 regularization is actually a slightly less aggressive. The L1 regularization is very aggressive. It is so aggressive that it can actually zero out features. What happens? If the feature isn't contributing substantially to the reduction of RSS, the model will set its coefficient to 0 and eliminate it from consideration. This is an automated feature removal process, right? L2 regularization, ridge regression, is an automated feature desensitizer, all right? Sensitivity, remember sensitivity on the confusion matrix? There's a relationship of attempting to minimize false negatives, right? We don't want anything that is, false positives, false positive. We don't want anything to be falsely positive, right? Or falsely negative. So false negatives are what? When it is a positive and it's been taken in consideration, false negative. So the ratio of sensitivity is false negative over true positive, true negative. That's what we call the sensitivity score. Why? Because the model is increased, it's incentivized to make sure that all of the positives get captured. All the variance of the positive class gets maximized. we put our finger on the scale toward the positive side and say, look, you need to make sure this false negatives are absolutely minimized. In this case, we're going to go the opposite direction. We're going to say, look, right, do it best you can with consideration of everything. Be ultimately equally fair with the L2 regularization, the ridge regression. The L1 regularization says minimize globally, minimize the whole value of the coefficient, just the sum of the absolute values of the coefficient. It doesn't matter which direction the slope is, right? It doesn't matter whether it's a negative or a positive coefficient, because you can have negative coefficients as well. But it's saying to decorrelate all of that stuff. Desensitize the model globally. It'll desensitize it so far that it literally stops responding to a feature. Like I said, it is a very aggressive methodology. It's very comparable to BIC in its productiveness with respect to feature removal, and that it will usually remove quite a few features depending on how much you iterate through it. But Lasso allows the model to selectively include or exclude samples based upon whatever it feels like doing at the moment, right? It will matter from set to set. So the weird thing is you won't get a consistent set if you use a very aggressive lambda with L1 regularization, because it will start to get rid of features that even do have some descriptive characteristics, just because of the fact that the penalty of having even a 0.001 for that coefficient is high, right? 0.001 times a lambda of 10, a scaling factor of 10, the importance of reducing the penalty. So this value here, this lambda factor penalty here, is the scaling factor for the summation. Make lambda high in L1 regularization, and you incentivize the model to remove even more features. It's kind of cool. I like this one because I think it usually does pretty well with paring down to the absolute minimum number, but it requires you to crank that lambda up pretty high, and it does have a set point, right? There's actually an ideal number. We're going to talk about this next time, but I'm going to mention it just in one very brief moment, and that is we're going to use cross-validation to determine the optimal number for lambda as a result of differential performance across different sets. So from one set to another set, its quality of removal or its quality of minimization with respect to its quality of fit, we can utilize that ratio to select the optimal number for lambda, such that we tell the model how much to penalize the coefficients so that it doesn't go overboard in removing too much, and so that it isn't too flimsy with respect to inclusion or respect to the regularization of the data. So these shrinkage methodologies are pretty powerful, and we use these across a lot of different metrics, including like neural networks and deep learning models can utilize shrinkage methods to eliminate complexity of the model down to where we pare down only to the absolute minimum number of parameters that we need in order for that model to be able to run. So,
is that because those models are so large?
Yeah, I know we talked about 30B, which is the newest. 30. They actually found another one. There's like 36B out there. 36 billion parameters.
It's insane.
It's nuts. There are tools. There are actually forms of this sort of process built into the flow of the system, so that it incentivizes the system to not get pulled away by any internal biases. They're sort of flow correctors, masks, internal flow masks, and annealing we use to do that process as well. So, where we change lambda parameters during the training process to try to see whether or not we can push it to remove more features, and then we'll crank it back sometimes to give it a little bit more capacity to be able to fit. So you can retrain modules of it. All right, thank you very much, guys. Sorry I didn't take too much extra time, but I'll see you guys on Monday. I'm going to try and get the labs worked out, so I won't probably post those until later on today. If I don't do it later on today, I'll do it Monday. Okay? I don't want to stretch you guys over the weekend as much as possible. We have about 2 weeks on those anyway. So it'll be bumping us up against.
Is it going to be highlighted 5 and 6?
5 and 6 are going to be together in one thing.
Oh, all of 5 and 6?
All of 5 and 6 are going to be together. I figured it actually made more sense because of how we're covering it. So, take care. Have a good weekend. Thank you.
Thank you.